Okay, so welcome back. We are continuing with pipe flow. We talked about laminar pipe flow last time, and this time we're going to have a couple lectures on different approaches to dealing with pipe flows. But just to start with, and a couple approaches, and also something I kind of found in the process of preparing these notes. A different way of approaching it than what the book actually does. Okay, for turbulent pipe flow, the velocity profile can be approximated with this log law. And the log is just U of R over friction velocity. Friction velocity is shear stress at the wall. And if you remember, shear stress at the wall is just the result of flow coming out in a pipe and sort of being stopped at the wall. And when it's stopped at the wall, you have essentially a shear stress that goes as du dy, just in the simple case, or r du r dr. There we go. Y is equal to r minus r in this particular case. Kappa is equal to 0.41. It's a von Karman constant. And B is equal to 5 for a log law constant. And you can integrate that and get a mean velocity or an average velocity within a pipe. And if you integrate it across, you end up with something that looks like this, which is V over U star, again, that friction velocity, 2.44 ln of R U star over nu, plus 1.34, and this is related to the Darcy friction factor. So if we affect the flow and we slow things down, velocity over U star becomes a square root of 8 over F. I'm not expecting you to derive the log law. I just want to make sure that you've seen it. The important difference here is what the profiles look like. And in the last couple lectures ago, we talked about this kinetic energy correction factor, alpha, and the reason why you do it when you have parabolic profiles, and that's a parabolic profile at the top, where you have a maximum velocity at the center and a decreasing velocity to the wall. And in all cases, they go to 0. However, when you have a turbulent profile, you have essentially a flat profile across most of the cross-section of the pipe. And so the velocity that's there is this pretty much the maximum velocity. It stays that way over a large region. There is a small region near the wall where you have fluid being slowed down. And that goes to your dimensional analysis where you talked about things like Reynolds number. Inertial effects are not as important in the top as they are in the bottom. Where this all leads is that we can start to look at pressure drops within pipes. And pressure drops, and using that information for the average velocity, friction factor, using a log law, you get Prandtl's law for smooth pipes. And it's 1 over square root F, 2 log of Reynolds number based on diameter, square root F minus 0.8. This is for turbulent flow in a smooth wall pipe. Smooth walls means that there's no roughness, nothing on the surface. It's an implicit equation because you have on both sides of the equation square root F. And it has to be solved iteratively for F if Reynolds number based on diameter is known. It's the basis of the smooth pipe curve on the Moody chart. And in a couple slides, I'll show you the Moody chart. For a limited range, 4,000 to 100,000 Reynolds number based on diameter, you can use a relationship for friction that's 0.316 Reynolds number based on diameter to the inverse quarter. So you can start to plot what you know. So you can see here results from Nicordazzi. And one thing is that U over U star shifts. So here is a couple parameters that are boundary layer parameters, so friction velocity, y plus, and things like that. Again, not important on their own. What is important is that you see a behavior that causes a shifting because of the introduction of roughness elements. So roughness elements just means that if I have a pipe that's like this, it's smooth if there's nothing on the pipe. But if I introduce very small elements along there, and they're not very high, they can be millimeters, they can be small percentages of the height of the roughness element can be a small percentage of the diameter, but they still affect things. And so you end up with the curve on the right. So the curve on the right, you're used to this. We talked about this. That's laminar flow. Here you have the smooth pipe relation. And here are different results, and it's friction number versus Reynolds number based on diameter. Different results for differing levels of roughness. So at the very top you have 0.03. At the very bottom you have 0.00099 of epsilon over d. Again, small roughness element, small height. These are, you can think about this as sort of sand grains thrown in a pipe. So you can have a 1 meter cross pipe with, sub-millimeter scale grain of roughness on it. So you have that sort of partial description. And what's really important is how the roughness element affects things. So very close to the wall, there's something called a viscous sublayer. And essentially, it's a blanket of fluid that is acting to isolate the wall from what's happening. So if you have a very thick viscous sublayer or very small roughness elements, and that orange line is the thickness of the viscous sublayer. So a boundary layer is viscous sublayer, a buffer layer, and then an outer region. It doesn't matter. The main thing is that right near the wall, there is a region of fluid with very, very slow motion. If it's very small, it's hydraulically smooth, and the roughness doesn't affect things because the fluid is able to go over the viscous sublayer. Transitional roughness, if I drop that orange line or raise the roughness height so that it's between a value of roughness of 5 to 70, friction depends on Reynolds number and the relative roughness epsilon over d. So it starts to affect things and it penetrates through there. Friction is independent when it's larger, so very thick boundary or a thick roughness. So if you try to imagine 10 centimeter roughness elements in a 1 meter pipe, you really aren't going to have an effect of friction that is independent of, or friction number is not going to be dependent on Reynolds number and only depends on the roughness. And the sublayer is gone. It doesn't exist, it just sort of moves through. In fully rough flows, viscosity and the Reynolds number, because again, Reynolds number back in chapter 5, inertia over viscosity, viscosity and Reynolds number no longer influence the flow, and the friction factor becomes constant for a relative roughness. And that function just becomes 1 over square root f minus 2 log of epsilon over d 3.7. And this corresponds to horizontal lines on the right side of the Moody chart, which I still haven't shown you. Now I haven't checked, so I'm going to say that it's in the book, but the Colebrook equation is in the book. If you want to solve for this, you can take the Colebrook-White equation, and you get 1 over square root minus 2 log epsilon over d 3.7 plus 2.51 over Reynolds number based on diameter square root f. And you can see immediately the problem is that if you try and solve that, you have f on both sides of the equation. It's implicit. And the answer so far has been to essentially chart all the values for a large number of friction factors, Reynolds numbers, and place that on something called a Moody chart. I'm also going to be using the Holland's explicit expression for a good part of this, and then at the very end, another one which I came across just recently and I kind of like, and has some interesting results. I'll also show some problems with the second one. But Holland has an explicit approximation, and it's 1 over square root f, which is minus 1.8 log epsilon over d, 3.7, 1.1 to the power 1.11, 6.9 over Reynolds number based on diameter. And it has a plus or minus 2% accuracy. Now, the problem, well, I'll talk about the problem. Here's the Moody chart. So this is the chart, and on the next exam, or on the final exam, I'll certainly have a Moody chart for you. You should be familiar with this. On the left-hand side, the y-axis is friction factor. On the lower axis, the x-axis, you have Reynolds number, and then you have a whole bunch of blue lines. And those blue lines correspond to different epsilons over d. And you can see it goes to a value of 0.05 to a value of 0.00001. Very high Reynolds numbers in this range, 10 to the 8th. Very relatively high friction factors. And it also includes this, which is the laminar case. It has the smooth pipe solution. And it also has a dashed line where you go from a curved relationship between epsilon over d and Reynolds number and a flat area where you have complete turbulence. So on the right-hand side of the dashed line, you can see that pretty much they're all flat. And I'm going to do some remarkable reading of this chart, and then I'm going to do it with the Holland equation and show you how you might be able to get remarkable readings off of this chart. But you can note that this is highly dependent on Reynolds number in a range that is 10 to the 8th to 3,000, 35, yeah, 3,500, 4,000, somewhere around there. And again, this is sort of that discussion we had at the very beginning where we said, hey, transition occurs at 4,000 and it's absolute, but here it's roughly 3,500. Okay. And it's all for a particular value of water. Feet per second, velocity feet per second, diameter inches, all of that stuff. You got to be really careful when you read the chart. Different types of pipe. And one of the things you'll see in a lot of different problems is that you're going to be dealing with steel, iron, asphalt, cast iron plate or pipes, where you get an estimate from this chart or this table of what the roughness is. So it's 0.00007 feet, 0.015 millimeters. So relatively small values. And what that translates to is a huge uncertainty. I mean, there's a huge uncertainty associated with it, but it really doesn't matter. Plus or minus 50% on this kind of number with your calculators is not going to affect your final results sufficiently that you're in the wrong physical regime. Where you are going to start seeing problems, and you should see, you can take a look at the text for all of these. You can use the Moody chart And for some reason, I don't think White's text uses Hallen's equation, but I think it might, so I don't remember, and I'm sorry, but Hallen's equation is good, and it's a better way to do this, but you can also use the Kullback equation if you want to iterate. Head loss problems, you are asked to find head loss, and you're given all the other parameters. Flow rate problems, find V or Q, you're given all of the rest of the parameters. Sizing problems, given all the rest of the parameters, find D. And then finally, length problems, no iteration needed. There you go. Type 2 to 3 problems are the most difficult because you have to go back to the chart and you have to iterate until you have a solution for the friction factor that is converged. And so you end up making a guess. Once you make that guess, you then solve it, and then you go back to the problem. So here is the first type, and that's type 1. I have compute the head loss and pressure drop in 61 meters of horizontal 15.24 centimeter asphalted cast iron pipe, carrying water at 20 degrees C with a mean velocity of 1.83 meters per second. You've got water, rho of 998 kilos per cubic meter, mu, which is 1.1 times 10 to the minus 3 Pascal seconds. And if you go back to that table that I showed you 4 or 5 slides ago, you also have an epsilon of 0.00012 meters. So it's 12 millimeters, or 0.012, it's something, I forget what it was. So we have all the terms, we're given all those parameters, and the only thing we really need to do here, so these are just standard definitions, is you have to calculate the Reynolds number. And you get roughly 2.77 times 10 to the 5th, which is high enough that it exceeds that 4,000 threshold that we've defined here, so we can say it's fully turbulent. So if it's fully turbulent, we have a relative roughness that we need to consider, epsilon over d. And you get a relative roughness of 0.000787. So very precise number, a very precise number on, well, I mean a reasonably precise number on Reynolds number. Let's continue. So the first way I'm going to do this, I'm just going to say, hey, let me use the Holland equation. I have epsilon over d. I have Reynolds number based on diameter. I've got everything that I need to fit into the equation. And one thing I should mention really quickly is that if you look at the H sheet, the Holland equation is already there. Reynolds number 2.8 times 10 to the 5th and 0.00008 or whatever number that you had, you get a friction factor of 0.197. Now, I took this from another example. So they said they read the Moody diagram and they extracted out a F by 2.8 times 10 to the 5th on the x-axis, epsilon of d on the roughness curve, and they extracted out 0.0198. Okay, so that's what I did. I went through, you've got 0.0008 right there. You have 2.8 times 10 to the 5th in there. And you're somewhere between 0.019 and 0.02. You're not at 0.02, but if I were to read that chart on my own, I would read it as 0.02. So as you go through this, one of the things that becomes very difficult is to get this kind of precision that you will see in the text when they talk about what they've read off the Moody diagram. I can't achieve the precision they have achieved. But all you're doing is 0.0008 Reynolds number on the chart, and recognize, first of all, that both this, all of the axes are log. So if you calculate it, you can use either value. It's pretty much the same. And then you get a head loss out of that by just substituting back into the equation FL over dV squared over 2G of 1.35 meters. So 1.35 meters, I'm using the Moody diagram number they got, but and delta P is equal to rho G HF, which is equal to So the final answer is really delta P is 13.2 kilopascals. Head loss is 1.35 meters. Any questions on that one? If you haven't figured it out, I'm not a big fan of reading tables or reading charts. You should try and use Howland equation, but you really have to use the Moody diagram afterwards. The Moody diagram has one advantage. You are not going to get the precision of 0.0198. Maybe you will. I can't do it. But good luck. But it will tell you whether your number is within the right ballpark. So generally what I would try and do is iterate on Howland or the Swami-Jain equation, which I'll show later, but then validate against what's happening on the Moody diagram. Again, oil. But now with a different, oil with density close to that of water, 950 kilos per cubic meter. New 10 to 2 times 10 to the minus 5 meters squared per second, flows through a 30 centimeter diameter pipe, 100 meters long with a head loss of 8 meters. The roughness ratio is 0.0002. Find the average V. And there are, I'm going to do it this way. I'll talk about an alternate way later. But I'm going to do it with validation or verifying with the Howland equation and also using the Moody diagram. So from the head loss equation, you have HF, F, L over D, V squared divided by 2G. You have the head loss that you're given. You have the friction factor, which you don't know. You have all the rest of the terms. And that yields FV squared equals to 0.471. So again, I'm going to try and set this up so that I reevaluate each time and ensure that I have a number that makes sense. And this time, my problem becomes I don't know velocity, I don't know friction factor, so I have two things that I'm going to iterate on, and then I'm going to calculate everything from there. So for the initial guess, at rough flow, I'm going to guess fully rough flow. I'm going to guess fully rough flow, start with that, and if I do that, I'm going to get a friction factor of about 0.14. I'll show you that on the Moody diagram. But first, let's just calculate what my velocity is and see what happens with that. So it's going to be 0.471 over 0.14 square rooted, which is approximately 5.8 meters per second. Calculate the Reynolds number. And I get 87,000. So let's look at what my initial guess looked like. So my initial guess is that I am in the fully turbulent region. It doesn't matter. I can extend the dashed green line a little bit more. But basically, I am at 0.014. So I look at, so the information I have at this point is just that it's 0.002 for epsilon. I have a Reynolds number that I'm going to guess is somewhere in this range over here, which is let me just make sure I'm in the right range. 10 million to 100 million. So it's very large. It's a very large guess. And clearly I'm wrong, because my Reynolds number based on this is 87,000, which means I need to reiterate on this. So if I do that, I can use the Holland equation, and I will get one over square root of f, which is equal to minus 1.8 log 0.0002 or 3.7, 1.11 plus 6.9 divided by 87,000. And that's equal to approximately 7.18. So F is equal to 1 over 7.18 squared, 0.0194. Okay, so that is an interesting sort of shift. It moves me well to the right, or left, excuse me, on this curve. So I'm moving up here somewhere, so I'm at 87,000, which is somewhere around here, and I'm getting somewhere around here. So if I use that updated Reynolds, or updated friction factor, I get V, which is equal to square root 471 over 0.194, 4.93 meters per second. So if I take my updated value and then I calculate what my